So for about 10 years, I'm in Parma now. And recently I started a collaboration with cosmologists, and they are interested in models for cold dark matter. And okay. So this is our cosmologist, Massimo Petroni. I thought we have some experience on numerics and we bring it together. Most of the work was done by Tim Zimmermann, who was a bachelor and master student in Heidelberg with me. Yeah, okay. Before I start, some advertisement. We have a PhD position, which will come out next week, just on this topic, and also a postdoc position on a topic which Julia just talked about, so open control of open quantum systems. And we are in particular interested in superadiabatic methods. Okay. So as a little motivation, there's some interest to, and that's also why I entered in this business, to get cosmological problems into the laboratory. Okay? Because of course it would be much easier to model the evolution, for instance, of dark matter in a BSc lab than just to study astrophysical data. Okay, so this is a bit the motivation of this work. And there are some, let's say, analog experiments. The system I will talk about is called Poisson or Newton-Schrödinger, so this is the same. Can, for instance, be modeled up to some degree in optics. So if you never heard of Segev, this is one of the top guys in doing classical and quantum optics, in doing simulations of more interesting systems like this one. Okay. There are other things like which can be modeled like expansions with BSCs. So here you see this exploding ring. The latest experiment in this direction was done in Heidelberg by Markus Oberthaler's group. They realized with some tricks curved space-time, so they could get essentially a Friedmann type of metric by modeling the spatial part and also the time part, which is interesting. So this is a bit the motivation of this talk. So can we think about realizing these models? I will show you now in a lab. Okay. The model, first of all, I don't know if I have to tell you about dark matter. I think it's quite established that our universe exists mainly of dark, then of visible matter. The major hint to this is more than 30 years old. If you measure the rotational velocity of stars in our galaxy as function of the distance of the center, this should go down because as the stars are more distant from the center of mass, there's less, so there's more attraction. Okay? But this does not happen. The further you go out, let's say that the velocity seems to saturate. So this means around us, there must be a halo which tears out the stars some way. So the experiment of this velocity tells us, the experimental data, that it goes more or less like this and doesn't go down as you would expect just looking at the visible stars. Okay, there are other hints by the background radiation, which I don't want to talk about. So most of the matter is actually dark matter. There's also dark energy, which is responsible for expansion, but that's another issue. I'm only interested in dark matter and in a specific model for dark matter, which has several motivations. One, it can be seen as a mean field model of many-body classical interacting systems, gravitatively interacting particles. And the other one, which is a bit more to my taste, is a non-relativistic limit of a many-body quantum field theory. So that we have axionic-like particle which has a certain mass. It's quantum, so it has a certain h bar. And the h bar, actually it's h bar over m over the mass is our parameter, which you can tune and then compare to observational data. The model we are using goes back to many works, but I think Widro Kaiser is the one usually cited of the early 90s. Okay. Since this paper, which is around 2000, the model we are studying is also known as fuzzy cold dark matter, cold because h bar is very small, so the Pauli wavelength is extremely large. So scales of galaxies or larger, okay. And fuzzy because it's, quantum mechanics is oscillating, so that's why it's fuzzy. Okay? So it's not classical. There's a paper which, with some issues, models actually this Poisson-Newton equation, which I will show you, and you can compare this to many body simulations. And the comparison is rather fine, but I think this picture has really been tuned because you can never statistically be sure where these meta peaks happen out of a essentially random background. So, talked a lot about motivation. So the equations we are using are those two. So we have a Schrödinger equation, a kinetic part and a potential. And now the interesting part is this potential is the solution of a Poisson equation. This is a Laplacian, which has as density the wave function density itself, minus the background. So we are not interested in the uniform background. We are interested only in the fluctuation, which gives this potential. Then with physical units, which I have no time to talk about, but it's omega, it's the dark matter part. H0 is the Hubble constant. We can rescale everything and get the dimensionless form of this equation, which you see here. Okay. Just a typical form, V is a potential depending on the density, which comes out of this. Okay. And then there's a second complication. It's not only highly nonlinear because of this Poisson solution, which you put into your Schrödinger. It has also a prefactor, which is time dependent. This prefactor, which is time dependent, starts at 0 and goes to 1. Some power law shape. The exact shape depends on the model for your metric, for your universe. Typically, it's power law, and it models essentially the expansion of space-time, so the spatial expansion of our universe. And this A of t makes actually the numerical simulations quite demanding. Okay? This is why we directly started from a one-dimensional model, not from a 3+1 universe, but a 1+1 universe. And yeah, it turned out that it's actually much harder than expected, but now we understand why. And this is what I want to talk to you. Okay. The numerical method we are using after some trials is essentially standard split step Fourier evolution. So we solve one part of the equation, evolve, then solve the other part equation, evolve, and go back and forth with Fourier transforms. Okay. This has the one advantage that it's norm conserving, which can be actually directly tested, or mass conserving, as cosmologists prefer. And it has the big advantage that it direct in Fourier space, the solution of the Poisson equation is trivial. Okay. And moreover, we know also the kernel, the Green's function of this part exactly analytically in any dimension. Okay. And this helps together with our method. So some numerical tests. So you like dynamics. So this is a phase space where we have a projection of our wave function into phase space. So this is P and X, so momentum or velocity and position. And here we put an initial Gaussian state, which then starts to be deformed. And then here, this is the crossover point when the problem gets nonlinear, and you see what forms a highly complex structure. So out of my initial state, there forms a highly complex structure, and the question is, where does the mass accumulate? Because it's attractive, it's gravitationally attractive, okay? And in which form does it accumulate? Does it form solitons? For instance, in 2D, it might form vortices and so on. Essentially, what we saw first, just doing numerical simulations on this equation, which you have seen before, there's actually no solid conic core forming because cosmology in 3D predicts there's a nice solitonic core, and this is stabilized by sending out matter. This is called as gravitational cooling. Okay? So it automatically stabilizes with a specific form which can be semi-analytically predicted. Okay, so interested in phase space and in dynamics, you can have a look at my book. In second edition, just appeared this year. So in this one-dimensional model, which is very simple, if you start out from a Gaussian initial state and keep this expansion factor constant to make things a bit simpler, you can study equilibration or thermalization. Okay, this is, for instance, an entropy quantity, so it somewhat thermalizes, so it stabilizes. Also in energy, but we never saw that the system goes into a stationary state. Okay. What does this mean? So I would, at some stage, I would expect that all the matter collapses in the center, like initial Gaussian, for instance. And then this is a double log plot of the density. So do you get a solitonic core and something outside, which is typically predicted as a power law. Okay. But none of the predictions, let's say here, these curves are fitted by our data, and also this data is actually oscillating in time quite a lot. And this took us a long time to understand. You can fit the tails, okay? There are some cosmological predictions, Navarro profiles are they called, with some power law tails, which I'm not so interested in at the moment. It's just the point which I would make, it never seems to collapse into a solitonic state. I can calculate this state numerically by doing imaginary time evolution. So I can predict it, but in the real time evolution, I never collapse to it. And do you know why? Okay. This has to do with fluid dynamics. So essentially this Poisson-Schrödinger problem, not exactly, but approximately maps to Vlasov equation. And it's well known mathematically that the Vlasov equation with long-range interaction has no stationary state. So there are no time scales or no scales in this system. And that's exactly what happens. So I told you that the Green's function of the Poisson problem, you know, analytically, that's the reduction into 1D of the 3D Green's function. And what you get is essentially a constant potential scaling with V proportional to X, where X is the distance from the mass center. So asymptotically, this is equal to the potential. The second part comes just because of our periodic boundary condition. So for a moment, you can forget this part. This means essentially that the force is constant, so it doesn't depend on distance. And that's an extremely long-range system. Okay. So this is a problem. So how can we nevertheless compare our 1+1 model to a realistic situation as predicted in 3D cosmology? And we came up with an artifact. So instead of saying, okay, my 3-dimensional world is open in the other 2 dimensions, we just use a confinement in the other 2 dimensions. Now you have to understand that the system is extremely nonlinear interacting via the density. This means if you use a confinement in the other 2 dimensions, this essentially rescales the mass in the direction of interest. For the quantum dynamics people, we rescale h bar. Okay, so this is essentially giving us a time scale. So introducing a transverse confinement gives me a time scale. Did I say time scale? A length scale. So I artificially put a length scale into a system which doesn't have one. Okay. But if we do this, so this is just to show you, this is the uniform case. This dashed line would be the three-dimensional gravitational potential. And with our confinement, we are approaching, depending on the confinement parameter, essentially this more three-dimensional type of potential solution. So these are simulations in the confined case. We have solitons. We have inelastic collisions, so of two solitons which form. But more interesting is this plot. This is a density as function of time. Here really x in x space and in time. So you really see this solitonic core forming, and here there's stuff going out and due to the periodic boundary coming in from the other side and might collide, as shown here, is the first part. Okay, so here, for instance, I don't know. I think this part is, I don't know where we are here. Okay. So now we see these solitonic cores, and we see also the what is called or known as gravitational cooling, that this solitonic core forms sending out mass or matter. And this is better seen in looking at the profile of such cores. Okay, they are now as predicted. Okay, so we have a solitonic core and a power law tail, and also the power law tail is as predicted as by cosmological theory. The only difficult or difference to the theory is that our exponent is different, but this is not a big surprise because we are nevertheless 1D plus something artificial is never exactly 3D. Okay. But this means our 1D naive model didn't have a length scale and did not go to a stationary state, while our confined model does. Okay. So for instance, in 1D I can also model radial symmetry situation where you have just one distance r, and then I get perfectly what you predict or what cosmologists would predict is r to the -3 scaling of the power law tail. This tail is essentially all this matter which is sent out, and what is left is this solitonic core. Okay, this picture sums up what I told you essentially. This is infinite confinement, essentially no confinement, intermediate confinement. So here you see two length scales. R is the range of the effective range of gravitational interaction, and sigma is the size of the solitonic core. So if I have no confinement, essentially, the solitonic core is always much bigger than my length scale, and I will never see it. In this case, okay, so this dashed line is always much larger than this, so I will never see it. On the other hand, going down here, this dashed line moves down, and then I'm able to see what I'm expected to see. This epsilon is essentially our confinement parameter, which scans from the free Poisson-Schrödinger solution to the confined solution. Okay. I will finish up with some numerical details if you're interested. Okay. What you can check in our calculations is the norm or mass conservation. We have a unitary system, then the momentum conservation, so the total momentum is also constant. What is not constant in the expanding universe, so if A is time dependent, is the energy of the system. But also this can be checked because you can add the energy loss, so to speak, or subtract the energy loss, so this is negative. And then if you check the energy plus the loss, you can define this quantity, which should be constant, and this can also be checked for various cases. So you see that it grows as function of time in the evolution, but it's always bounded by 10 to the minus 3 or something. So the energy, so the expansion is considered, but in this sense, the total energy is nevertheless confined, and so we don't introduce numerical artifacts. Okay. Our last advance was using an adaptive time stepper in our model, and this helps to speed up the evolutions by a factor up to 100, which gives some hope to extend this problem also to 2 + 1 dimension, which is of course quadratically harder. So I showed you converged numerical results on a 1 + 1 or one-dimensional Schrödinger-Poisson evolution. We checked in detail the precision, particularly for expanding universes. Our method is compared with a basis function approach using B-splines, and this works well for small boxes. So we have a comparison. So we are sure that we are doing the right stuff. The question is, can we do this in 2 + 1 and study the corresponding parts of solitons or vortex evolutions? And this would be this PHP project I've shown you. Okay. I thank you for your attention. Here are our papers. So this is to come on the numerical aspects, and this is more on the physical aspects of this quantum simulation of cold dark matter. So thank you very much.
One quick question, if you have a question. Okay, thanks.